Welcome. So far in the course, we've talked a lot about charge. Now we want to talk about charge in motion. Charge in motion is what we call electric current. It's the flow of charge. The symbol for current, it's not C. We've already used that extensively. It's I. Ampere chose the letter I because Ampere thought of it as the intensity of the current. We typically don't think of electric current as intensity, at least in English we don't. But that capital I is the symbol chosen by Ampere for current. It's equal to the charge per time, where delta Q represents an increment of charge, delta T, interval of time. So some increment of charge per time that passes through an area. Now, why an area? Don't we go talk about a wire? Well, a wire has the cross-sectional area. Don't think of current as the velocity of a charge. An analogy would be to think of water. If you have a squirt gun, you might be able to spray a stream of water at a high velocity out of that squirt gun. But that's a small flow. Whereas a fire hose may be a similar velocity but a very large flow. A river may be a very slow velocity but a large amount of water because of a large cross-sectional area. So it's the amount of material moving through an area per time, or amount of charge moving through an area per time. The unit of current is coulomb per second, which is called the ampere, named after the French mathematical physicist Marie Ampere. Almost no one says ampere. Typically, current people say amp for short, or for a smaller amount, they'll say milliamp. Usually it gets truncated. An important thing to notice, current delta Q per delta T. A positive current means we're referring to positive charge flow. Of course, delta T is going to be positive, so delta Q is positive for a positive current. We know in a wire it is electrons that move in the wire. I've discussed before, I'm going to discuss again in this video. We pretend that positive charges are moving. We can do that because if electrons move one way, it can be treated most of the time as equivalent to positive going the opposite way. So yes, we know electrons move in wires, but we treat it as positive charge flow. Here's a picture I've shown previously when we talked about capacitor. I'm going to show it again just to emphasize the point. We have two plates, metal plates. Both of them are neutral. Both have 3 negative, 3 positive. Now, of course, in reality, you'd have a vast number of nuclei and electrons making up a metal. This is just for illustration. Equal amount of positive and negative, 2 neutral plates. To move the electrons, you have to supply some energy. And typically we're talking about battery, or often or more commonly it may be a power supply. It takes energy. Why does it take energy? Well, look at the plate on the right. It's neutral. If I remove 2 electrons, I'm taking negative charges away from something that is positive. I'm pulling away something from something it's attracted to. It takes energy. On the other hand, if I place those negative charges on, I leave a positive charge there. If I place those negative charges on the other plate, I'm putting the negative charges on something that is now negative. So that takes energy. The point is, what happened? What happened was negative charges went from the right side to the left side. But if we look at a piece of metal, we can't see those electrons. We can't see those nuclei. The result is we know one becomes negatively charged, one becomes positively charged. So we pretend that, oh, positive charge must have gone from the left to the right, when in reality it was negative going from right to left. Electrons move left, the right side becomes positive. Let's look at an example. Okay, this cylinder is to illustrate a wire. Wires typically are cylindrical. Of course, they're long and narrow, but illustrate a cylinder. So this illustrates a metal wire. Now, the nuclei, which are positive, are fixed in place in what's called the lattice that makes up the material. That's why it's a solid. If the nuclei can move, it wouldn't be a solid. It'd have to be a liquid or gas. But the fact that the nuclei are fixed in place means it's a solid. For an insulator, the electrons would move locally, but not, from end to end. In a metal, electrons can move from one end to the other. So let's imagine what will happen if we put an electric field on a conductor. The electric field goes from left to right. The electric field, remember, is the direction of the force, positive charge. Therefore, we consider current as positive charge flow. The current will also be left to right. We can't see inside of a wire, but we would know you put that field across there, you get that current. By the way, how would you put a field? Remember, field, you have to have a change in voltage. Field goes from high to low. You'd want to put a high potential on the left side of the wire and a lower potential on the right side of the wire. That delta V over distance, electric field minus delta V over, say, delta X, electric field from left to right. But if I could look inside that wire, just at the atomic particles, what would I see? What I would see, the electrons are moving left. I say the current goes to the right, but those negative charges are moving to the left in the wire. Only the electrons move. Now, you can say, well, doesn't the field have a force on the positive? Yes, but they're not free to move. Only the electrons are free to move in the metal. Okay, let's do a little calculation here to illustrate how many electrons are involved. Suppose we have a current that is 80 MA. MA stands for milliamp. Milliampere, most people say milliamp. How many coulombs would go through that wire in 10 minutes? Coulombs of charge. How many electrons went through that wire in 10 minutes? Let's bring up the whiteboard. Remember, current, capital I, equals delta Q over delta T. Therefore, delta Q, the amount of charge, is equal to the current times the time. Current is charge per time. You multiply by time, you get charge. Delta Q is I delta T. So the current I, 80 milliamps, will be 80 times 10 to the minus 3 coulomb per second. 10 to the minus 3 for milli, coulomb per second for the amp. Delta T is 10 minutes. Of course, my current is per second, so I have to convert. And it's always good to use dimensional analysis. What do I have to do to get the right units at the end? I want to cancel out second. I want to cancel out minute. Get coulomb. So I'm going to say 10 minutes times 60 seconds per minute. Cancels out the minute. I have second on top, on bottom. They cancel out. 60 times 10 times 80 times 10 to the minus 3, 48 coulomb. Use a calculator, or this one you can just work out on paper. Okay, 48 coulombs. That's the amount of charge that went through the wire in 10 minutes. How many electrons? The electrons are negative particles, but we pretend that they're positive particles going the other way. If this current was flowing from left to right, reality, electrons are going from right to left. We're going to pretend that, for every electron that goes left, it was as though a positive charge went right. So we say this increment of charge, delta Q, equals some number n times elementary charge, Q sub e. Now the electron is negative. We're taking Q sub e as a positive number because we're pretending the current was made up of positive particles. So we're going to solve for n. N will be that increment of charge, delta Q, 48 coulombs, divided by the smallest charge we take, pretending it's positive, 1.6 times 10 to the minus 19. We get an answer. 3 times 10 to the 20 charges went through the wire. We pretend 3 times 10 to the 20 may have gone right. It was really 3 times 10 to the 20 electrons went left. But clearly a vast number of particles. Therefore, we're typically not going to refer to electrons. We're going to refer to coulombs and amps and milliamps because the numbers of charges are so vast. Because the 80 milliamp is not an extremely large current. It's the kind of current you might use working in lab. Okay. What about a current in a liquid? Now, typically, we're not talking about electrons as the charge carriers. We're talking about dissolved ions. If something dissolves in water to form ions, positive and negative, we call that material an electrolyte. Something that divides into ions, into electrical particles in water, an electrolyte. So that photo on the right is of a typical car battery, typical 12-volt car battery, so-called lead acid battery. A lot of what's in the liquid, there are many constituents, but a lot of it is sulfuric acid dissolved in water. We'll ignore the lead and so forth. So if you look on the left, that illustration, the H2O is water, the water molecules. Sulfuric acid divides into what's called hydronium, H3O+. Basically, it's a proton attached to a water molecule. The other part of the sulfuric acid is sulfate ion, double minus. You could put a 2 minus, or sometimes what looks like an equal sign, 2 minus. You notice the positive charge moves up, the sulfate negative moves down. what's the direction of current? The direction of current. Think about it. Say, well, are those two canceling? No. Positive charge moving up would be a current flowing up. Negative going down, you would pretend positive going up. So in this case, if a single positive went up, double negative went down, it's as though we would pretend 3 positives went up. So in the liquid, you have conductivity from ions that move between the water molecules. This battery can put out a large current of the order of amps. Large current to start a car engine, gasoline engine. So you can have a large current from these ions in liquid. We're not talking about electrons in a wire. Ions moving through water. Now, as you can imagine, it's a somewhat constrained movement. The ions are much bigger than electrons. They have to squeeze between and around water molecules. So the current is not as easy as it is for an electron in a wire. But you can get a substantial current nonetheless. So you have a current in the solid, that's electron in a metal. In a liquid, it's ions. What about current in the gas phase? We have current in the gas phase. We have to have charges that can move. This is how we get charges in the gas phase. You have to create ions. Lightning is a situation where you have such an enormous potential difference between cloud and earth that it ionizes the air. Dielectric breakdown. This means the potential difference has to be so great you can ionize air, ionize the molecules that make up the air. That potential difference has to be of the order of a few million volts per meter. A few million volts per meter. So you have to have a tremendous amount of charge up in that cloud to give you such a potential difference between the cloud and the earth. It ionizes the air. Once it's ionized, through this breakdown, you have a current that can flow. And that's what the lightning bolt, lightning strike is. It's current flowing along a path of ionized air. Okay, so how does all that charge get on that cloud? Well, go back to our very first lecture, triboelectricity. You have hot air rising, you have cool air falling, you have moisture, maybe precipitating, moving through the atmosphere, a lot of things rubbing against one another. And we have to have different things. You have this moisture, you may have air rising, air falling, you may have suspended droplets. This rubbing, this triboelectric effect, creates tremendous charge separation. Then you get a difference from the cloud and the earth, you get a lightning bolt. So the conductivity can be from electrons and ions moving through the gas. Now, much more common, lightning is common, but much more than that is the fluorescent light. Fluorescent light, you typically have a long tube. You have an electrode at either end. You put a potential difference across the ends of the tube. Electrons are accelerated from one end toward the other end. Where does the light come from? Those electrons, as they're accelerated from the negative electrode toward the positive, collide with what is shown there as Hg. Hg is vaporized mercury. Mercury is a metal that has a vapor pressure. It's also liquid, hazardous material to work with. When the electrons collide with those mercury atoms, the energy of the collision can excite mercury atom to a higher energy level. The way that mercury atom returns to its ground state is by emitting a photon, emitting light. The light from those electronic transitions is ultraviolet. That's not going to be very useful for illuminating a room and so forth. So that tube has a white powder, absorbs the ultraviolet light, emits visible light. So you have a current flowing through that tube, current of electrons colliding with the mercury, and collisions, you're emitting light from the ultraviolet from the mercury, absorbed by the powder, then the white powder, and then it gives off visible light. Okay. And also those polarity can be changing from left to right with alternating current. Okay. So what drives the current? Well, here's an expression we've used before. Electric force equal to QE. It's the electric field acting on a charge. Electric force equal to QE. Electric field acting on a charge. Where do we get the electric field? Well, in 3 dimensions, each component minus the change in voltage with, say, delta x for the x component, delta y for the y component, etc. You need a potential difference, a delta V, across some distance, whether it's a metal, whether it's liquid, whether it's a gas, and of course, you need to have charges that can move. You put a potential difference in air, you're not going to get a current unless there are charges. So let's think about the current. If the electric field creates the force equals Q times Z, and delta V will also contribute, through the field to moving charge creating current. So here's going to be the expression we start with. Current equal to delta V over R. The larger the delta V, the bigger the current. You see it right there. The larger delta V is, the larger the electric field, the larger the force, the larger the current. So current is equal to delta V over some number R. R is the resistance to the flow of the current. The way to think about it, delta V is what drives the current. R is what resists the current. R is the friction serves as the friction in the circuit. Do not think of delta V as a force. That's why I like this slide. In the past, sometimes delta V was called electromotive force. No. Look at the relationship here. Delta V contributes to the electric field. Electric field times charge gives you the force. So that's the relationship between potential difference and force. But we formulated the current equal to delta V over R. The bigger the delta V, the bigger the current. R, like the friction, the bigger the R, it's in the denominator, the smaller the current. Okay, this relationship, this current equals delta V over R, you'll see leads to what we call Ohm's law, which we'll talk about in subsequent video. I thank you once again for watching all the way to the end.